Is that okay? So you've got the idea that you can write it in words. When there's an unbalanced force acting, it's going to
accelerate.
Accelerate, yeah. And the size of that acceleration is proportional to the force. So if you double the force, you get double acceleration. But it's inversely proportional to the mass. If one goes up, the other one goes down. So I'm going to ask that question again. When the mass is 10 times bigger, what does the acceleration do?
Goes down.
Goes down. It's got more mass, it's got more inertia, it's harder to move, harder to accelerate. So 10 times the mass here, you would get 1/10. And you can look at it like this, that if it's like this, increasing that mass by 10 should give you a 10th there, shouldn't it?
Yeah.
Yes? If you increase it by 10, you'll get 1/10 acceleration. So just bear that in mind. So sometimes the questions are about proportionality, and sometimes they're about explaining things, but other times it's actually calculations. So this one here, you've got the word version of it and the actual formula version. Is that okay? Now, if you get questions like this here, you've got a car there being accelerated by a force from the engine, 4,000 newtons, pushing it to your right. Okay? That's the arrow. You've also got a friction force pulling it back to the left of 1,000 newtons. So, when you come to use this question that says find the acceleration, A equals F over m, the second law, you need to decide what force am I going to put in there. So, Simon, do I put the 4,000 newtons in there? No. Do I put the 1,000 one in there then?
No.
Which one do I put in there?
3,000.
Excellent, because it's the unbalanced force. This is the unbalanced force, the overall force. You must work out the overall force first if it's not given to you the question. So 4,000 right, 1,000 left, 3,000 to the right. So that's what's got to go in there. Okay? 3,000 newtons to the right. What's the mass of this car? 1,500. Good.
1,500.
So, check your calculator, you'll get 2 metres per second to the right in the direction of the unbalanced force. So sometimes you get questions like that in the test or in your end of chapter questions. Is that okay so far?
Do you have to put the arrow direction?
No, you don't normally have to do it unless they actually ask you to.
Oh,
Okay. So I'm just pointing that out. So that's the sort of question you get, or they'll ask you about proportionality and like this. Now, the third law is different. Can anyone tell me the third law, please?
Yes. If there is a reaction force, there'll be an equal and opposite reaction.
Good. So there's an action force acting on one thing. There should be a reaction force coming back to the other object. So there's a few ways you can say that, okay? If you look at this one here, that's one way of saying it. If an object exerts a force on another object, the second object exerts an equal force in the opposite direction back. In other words, if you push an object, you get an equal force back on the second. Okay? They're always in equal and opposite pairs, or action equals reaction.
Well, then wouldn't nothing move if they had the same force coming back?
They're on different objects. So when one object exerts a force on the other object exerts an equal force back. So you can see this with some carts here. If you actually load one of these carts up and get it there, and you actually hit this thing here. So that cart, spring-loaded, pushed the first cart forward. What did the first cart do back to the second cart?
Pushed it
back, yeah, with an equal force?
Yes.
Yeah, in the opposite direction?
Yes.
Always?
Yes.
Always.
Yes. Wait, so if I push Simo...
You'll get an equal force back. You should be able to feel you pushing against Simo.
Oh, yeah. I won't move.
Yeah, you'll feel it. Like
you go back a bit, yeah.
So it says the laws are always saying equal forces, opposite directions, always equal pairs. No matter what the objects are, equal sizes. Okay? Now, I'm going to ask you a slightly more confusing one.
So it's like when you try to push a wall, you can't do it.
If you go and load a weight on one of these now,
Oh, that's going to be funny as...
okay, if you load a weight on this here and you do the same experiment and you go and do it like that,
should have put the weight on the other one.
does that one actually still experience an equal force?
Yes.
Does anyone think it doesn't? Oscar, does anyone think it doesn't experience an equal force? When I do that one there, different masses. Is the force still the same?
Yes.
Yeah, they are. Because this says it's always going to do this. It's always an equal and opposite force. So, did they have the same acceleration?
No.
Which one had the lower acceleration?
The one with the weight on it.
Yeah, the one with more mass. And the reason for that is based on the second law, isn't it? Because don't forget that if you have something with more mass down here and you make this bigger, the acceleration is going to go smaller because they're inversely proportional.
Yes.
Okay. In actual fact, if you increase the mass by 6 times, it should have 1/6 of acceleration. I think I'll actually just increase it by about 10 actually. So has everyone got that as a clear idea?
Yeah. Can you go back to the slide though?
The slide?
Guys, leave me alone.
So is it okay there?
Yeah.
So let's just do some examples of this thing here. If you take a hammer and you actually hit a nail down, there is a force of the hammer on the nail. Hammer on the nail going down. Let's say it was 10 newtons. So therefore there should be a force of the nail on the
Hammer.
Force of the
I
nail
thought like recoils.
on the hammer.
That's exactly what I was about to say. Recoil.
So those two there should be equal and they should be opposite according to the third law.
Yes.
The effect of the nail, of course, is the force going in that direction and on that object pushes the nail down. There's an overall force on the nail. But there's also an overall force on the hammer that causes it to
Go
Lift
on.
up when you hit it.
well, what does it do
Recoil.
first?
Recoil.
Yeah, well, it slows it down first, stops it, then it might bounce back.
Yeah.
Okay? But that's a perfect example of it. If you're actually in a pool and you start swimming and pushing water backwards, there's a force of you pushing the water back. The water pushes you forwards. If a rocket shoots gas out the back, it will go forwards. If you have, what else we got there? If you have these two carts here, obviously one cart's pushing the other one forwards like that. But there's an equal force on this one pushing it backwards. The forces do not cancel out off because they're on different objects. Okay, this force acts on this object, this one acts on this object. If I get a car and I get a windscreen and we run into a little fly or something, we're driving 100 k's an hour.
That fly, no, that car's going to be.
That's going to be.
How does the force of the car on the fly compared to the fly on the car?
The car's
bit
going to
Which
go
one's bigger?
The car.
Now, car's going to come up at second best. I'm going to ask you this question again. Which force is bigger, the one on the car or the one on the fly, or are they the
They're
same?
equal.
They're equal, yeah, they're equal. Okay? The forces are equal because of the third law. But this has got such a tiny mass, the acceleration on that fly is going to be
minimal.
Little.
for a small tiny mass, it's going to be acceleration which is huge. Okay, a little tiny mass, it's going to accelerate in one direction very quickly, enough to actually just splatter it into little bits of liquid, okay?
That's funny as.
Acceleration of the car, the deceleration of the car, not noticeable. You're not going to go, oh look, I've just hit a fly, I've slowed down. You're not going to notice that. If you hit a kangaroo, it's different, okay? But fly,
No, not really. The kangaroo just goes.
if you step out of the boat, there's a force forward on you to push you forward as you go like that. What does the boat do?
Goes backwards.
Yeah, it goes backwards, yes. Now, it won't be as noticeable. Sorry, the boat will go backwards here because this is a rowboat, it's pretty light. But if you're going to do this from a ship, would you notice it?
No.
No, the ship, you're not going to go, oh, the ship's gone backwards and stepped out. It's got a huge mass.